So the variational method is very simple, dirty, but powerful. So it relies on one theorem, meaning that you are given a problem, a Hamiltonian, you can make a guess, your own choice of a trial wave function that you think is quite close to the ground state wave function. Anything will do. Then you calculate the expectation value with respect to your trial wave function. The theorem says the number you get will be bigger or equal to the actual ground state energy. The equal sign, you can get it by luck if your trial wave function happens to be of the form of the exact ground state wave function, okay? And that lays the foundation for a lot of variations on this theme. For example, we can keep on trying different trial wave functions and look for the lowest expectation value that will be nearest to the actual ground state. So last time I introduced the idea that we can insert a parameter called the variational parameter into your trial wave function. Thereby, you can make infinite trials in one shot, okay? And I give you an example, okay? This is the harmonic oscillator. Let's say we forgot the solution, and then we make a trial wave function of one cosine wave using a parameter lambda to tune the width. Small lambda means wider cosine. Bigger lambda means narrower cosine. And we discussed the physics. We know that somewhere in between the very narrow and the very wide limit, there is an optimum shape. And we look for this lambda by first calculating the expectation value, which will give us a function of lambda. So thereby, we are actually doing many trial wave functions in one shot using lambda as the tuning parameter. Then we look for the minimum, and at the end, we get at a value that is 14% higher than the actual ground state energy. Thanks to a student, he pointed out to me that this shouldn't be here. This is extra term, okay? So erase it. I will make the correction later, okay? And here is some other examples, all right? So that is where we stop. So here is a very important example. I haven't carried out the calculation for you, okay? And I encourage you to do it yourself. But that takes us to the next important technique in variational calculation. And that will help us understand atoms bonding in molecules in particular, okay? So pay attention to this particular example. Here is another simple thing. Infinite well, 1D. Of course, you don't need this approximation method. You know how to solve it exactly. Let's say we forgot. Then we can think about, what does the ground state wave function look like? Then you can make a lot of argument about this is symmetric about the middle. Thereby, the ground state better be symmetric as well. For 1D problems, there's some property like that. And then the wave function should be 0 outside the well. So less than 0, bigger than A, because it is infinite potential energy here, okay? So we have this idea, symmetric about the center, 0 out there, okay? So one possibility, something look like that, is x times A minus x, okay? So x is this dashed line increasing with a minus x is the other dashed line that drop with a linearly. If you multiply these two things together, it has our expected property. Symmetric in the middle, drop out, and zero outside the well. That looks okay, right? Now we want to have to do a variational calculation by mixing this with another similar function. Let's say x squared, okay? So x squared, you have a quadratic increasing thing, and then you have something dropping, not linearly, something like that. You multiply together, again, it has something of the same expected form, okay? So now, maybe we can do a linear combinations of this reasonable two functions, all right? And then with coefficients C1 and C2. And now we have C1, C2 that can be used as variational parameters. So for this, you can take this, use the Hamiltonian, you have the kinetic energy term, minus h bar squared over 2m second derivative, okay? So you can do that within the well using this trial wave function, and then use C1, C2 as the variational parameter, and then you can try to minimize the energy. I tell you the end result. This is the end result. And if you look up the exact expression, you know this is the ground state energy. If I write h bars in terms of h, 1/8 is the exact value, okay? That is a unit, h squared over ma squared, okay? So it is 0.125. Now, even you forgot about the exact solution, if you know how to do a rational calculation, well, you are only, I don't know, less than 1% to the exact value. So that is pretty impressive, okay? Now, secondly, the theorem works. What you get must be greater than the actual one, okay? But this one is really good. Notice that it's not very laborious, okay? Not a lot of work, just a very simple calculation. But that takes us to a question, okay? We will explore a few pages later. This trial wave function is a linear combination of functions, okay? So can we set up the variational calculation in a general way in which the trial wave function is a linear combination of several functions? We will make use of this kind of form of trial wave function many, many times, okay? We will do that a few pages later, and that is the most important application of variational calculations. Some other standard problem I encourage you to try. A hydrogen atom. Try something like this. Does it work? Okay, so try it. Okay. Of course, you will get a number, and then you can compare with minus 13.6 eV. See whether how good or how bad it is. And how about a quartic problem that you are doing? I think you are doing it in problem set 1. Okay. And how about this infinite well with a tilted potential energy inside the well? All right. So this is not easy to solve. Nonetheless, we know this problem, and we have some quantum sense. For example, if you are going to guess the ground state energy of this well, so pay attention to some quantum sense, this side has lower potential energy, than the other half of the well. If it is flat, we know the ground state energy is symmetric about the middle. It's a sine wave, okay? Now, given that this side has a lower potential energy, and ground state means the lowest possible energy eigenstate, thereby the particle, the wave function, should make use of the lower side of the potential energy well more than the higher side, so as to get the expectation value of the energy, the Hamiltonian lower ground state, okay? So an educated guess would be the wave function will no longer be symmetric about the middle, but instead slightly tilted to the left-hand side where the potential well is lowered, okay? So do you understand this quantum sense argument? Okay, is that okay? Now, with this sense already built in, then now you can think about a trial wave function that look like this, okay? Now, this problem is rather like this, except for the tilted bottom, okay? So, the ground state will be symmetric like this, but this is not all that we want. We want it to be tilted to the left-hand side. But we also know the first excited state of this infinite well problem, right? It is this second sine wave, this one, okay? Now this one is positive on the left, negative on the right. So if we add this to the ground state, the left-hand side will be enhanced. The right-hand side half of the well will be suppressed, the wave function, the total, okay? So thereby, the probability wave function square will have our desired form. It will be more chance, there will be more chance to find the particle on the left-hand side of the well than the right-hand side. So with that sense, we need to tune the weighting. How much ground state will be used, how much first excited state will be used, or if you want to use higher excited state, what are the coefficients? So again, we encounter the same thing. The trial wave function will be a linear combination of functions, okay? And at that, after you do that, you have several parameters that you can make use of as the trial wave function, okay? As the variational parameters. So that is the idea, okay? Therefore, we have motivated, again, this kind of trial wave function form, okay? If you are more ambitious, you can use more than 100, again, sometimes we call it basis functions, that you want to decorate by the coefficients into your trial wave function. Therefore, you have many variational parameters, okay? So last time, a student asked whether we can have trial wave function of more than one variational parameter. Yes, indeed. So here you see many, okay? And even more ambitious. For this problem, if we take the infinite many eigenstate of this known problem and do linear combination to it, it will be an exact expansion for the eigenstate of this problem. Okay, so if we are ambitious sufficiently, if we write down something like this to infinity, suddenly it becomes our first discussion last week, writing the Hamiltonian into a huge matrix problem. So you see, variational calculation, which is an approximation and can be connected to the exact form, okay, if you use a complete set. Okay, so there's some connection, and that connection is important in later discussions. And now is the most important section for this method. Here, I would like to do a general discussion on a trial wave function of this form, linear combination of several functions. Here, generally, it could be n functions, all right? But I would like to do the derivation for the simplest case only, so that you can generalize it to 3 functions, 4 functions, 8 functions by yourself, okay? All these numbers are important in understanding molecules. So I have a trial wave function phi, which is C1 phi1 plus C2 phi2. Phi1, phi2 are known, is your selection. C1, C2 are meant to be used as variational parameters. Actually, in quantum mechanics, C1, C2 are in general complex. The trial wave function can be complex, but the meaning of quantum mechanics is attached to the wave function square. Okay, so it doesn't matter. I do this minimum, the smallest size, because I want to write shorter equations. Okay, but it's easy to generalize it to a bigger set. Now I will carry out the derivation in the most explicit way, okay, so that you can see through the mathematics and take the final answer with you. Let's do the variational calculation. We need this expectation value of Hamiltonian with respect to what we tried, okay? Definition is do this, numerator and denominator, okay? So let's do it step by step. Let's look at the numerator, okay? Now, we have to do this again and again in quantum mechanics in many occasions. So pay attention and get it once and for all. Numerator, okay? Now, this symbol means our trial wave function on the left with a complex conjugate, our trial wave function on the right without the complex conjugate, and whatever problem we are trying, the Hamiltonian in the middle. Okay, so you follow me? Is that okay? Okay. Now, make use of your inspection. There are some friends we met before last week. First, do you see that there are 4 terms? Right? This, integration will be 1 term, etc. Okay? Now, there are friends that we met. By that we mean, how about this? Phi1 star h, phi1 integration. We met similar expression last week when we write something into a big matrix. We will call it a matrix element using the label here. The left one is 1, the right hand one is 1. We will call it H11. Okay, do you follow what I'm saying? Because usually if I have a classroom, I will not show this to you. I will do it on the board. Okay. Now I need you to follow me closer in mind. Is that okay? Similarly, you will see 1 star H2. So that will be H12, H21, and H22. Okay? Collecting the coefficient, you will see C1 star C1 for H11, etc. Okay, so I hope that the second line is natural to you. Do you follow? I haven't made explicit use of the relationship between H12 and H21. Okay, so I leave it general, just pretending that I don't know there are some relationship, Hermitian, because H is Hermitian. Okay, I don't use that explicitly here. Okay, later on for convenience that will be useful. All right, now go to the denominator. You can do similar things, right? By definition, trial wave function star, trial wave function integral. Now, dear friends, we met. Phi1 star phi1 integration is our old friend S11. Get me? So in the same way, there are also 4 terms as listed here. Okay? So rather familiar, okay, all the symbols. So we are done. The expectation value with respect to our tri-wave function of linear combination of 2 functions is given by, this is what we want. It is a function of the variational parameter C1, C2, so I explicitly write it down here. And if you like, emphasizing the generality that they can be complex, actually they are, you see explicitly that they depend on C1, C1 star, C2, C2 star. Explicitly, it is this 4 terms over 4 terms. Okay, so any question about the algebra this page? Is that transparent enough? Okay, now we are not done yet. Okay, pay attention. We want to find C1, C2 such that partial E, partial C1 star, for example, is 0. That will signal that E is an extremum. Okay? And hopefully, well, usually it's a minimum. Get me? Okay? So we are halfway through. We need to do some partial derivative such that partial this symbol E, partial C1 star or partial C2 star is 0. Okay? That is the step of carrying out the variational calculation. All right? So here, instead of this clumsy expectation value symbol, I introduce E here. Okay? It is identical to what we just we used to write. Okay, so this is the expression to the next page. Okay, carry to the next page. Now, if you because Professor Liu introduced some matrix form of handling quantum mechanics, I read his notes and I enjoy it. Okay, so for those who like to do things in matrix, just to show you the numerator, this one. Okay, in the basis of phi1, phi2, your trial wave function can be written as C1, C2, the coefficients, because behind the scene, you know you have chosen phi1, phi2 as the basis. Therefore, what we call the phi star will be C1 star, C2 star, but in a row, okay? And the H in between, written into the basis that you have chosen, will be this matrix. You do this matrix multiplication, you will get the numerator, okay? And similarly for the denominator, okay? So if you don't like this page, fine. If you follow this, everything is fine, okay? Don't worry. Now, we need to find the best value or the optimum value, okay, of C1, C2, so that the expectation value is minimized. Now, I suggest, okay, and you may check it over, okay, that we can take C1 star and C2 star as the variational parameters. Now, some of you may object. There's still C1, C2. Can we take that? Fine. I suggest you to do that as well. I claim it will be sufficient to vary C1 star and C2 star, and you will get two equations. If you do the other two, of course you will get another two equations, but that other two will be redundant with the two that I've written down below, okay? So therefore, let's just do the minimum stuff. So I will take C1 star and C2 star as our independent variational parameters. So how to do that? I take this. Instead of keeping something in the denominator that when we do derivative will be clumsy, I multiply this. I multiply this to the left-hand side. So I have E times the numerator equal the E times the denominator equal the numerator. Okay, so this is this line, E times the denominator equal the numerator. Okay, now I start doing things. Take the partial derivative of C1 star. Okay, now follow me, please. Immediately in one line, we can write down the equation if you follow the thought. This is the only enemy. Okay, so the first term, we have something to D. After doing that, you pick up the rest. Okay, the second term has something to D, you pick up this. The third term, you don't have C1 star, is 0. The fourth term, you don't have C1 star, 0. Okay, therefore, left-hand side, you have that. Okay, follow me? Okay. Now, right-hand side, actually this itself should be a function, right? So we have partial E, partial C1 star, multiply into all this. But what we are looking for is to minimize E. So this derivative should better be 0. So we set that to 0, and that is the minimization process. So that term vanishes. Therefore, E in the rest of the partial derivative will be taken as a constant, okay? And now C1 star appear here. It pick up C1 S11, this one. Then the second term pick up C2 S12, this one. The rest don't have C1 star, disappear. Okay, so immediately you have this equation. Okay. Okay. Now we can do the same thing for C2 star. Again, train yourself to read out the answer, okay? Or at most, do it once and take the answer for the remaining of your life, okay? You don't waste time to keep on deriving the same thing again and again, okay? Although that will be comfortable, huh? Why we take C1 to be independent of C1 star? Okay, as I said, if you are not comfortable, try it out yourself. You can try real part C1, imaginary part C1, real part C2, imaginary part C2. Okay, Gawai. Okay, naturally that will be the choice. You have 4, I can interchange it with other 4, C1, C1 star, C2, C2 star. 4, 4, nothing. Okay, 4 to 4, fair. Now I'm claiming if I only do C1 star, C2 star, I get 2 equations. I encourage you to try C1, C2. You will get 2 other equations. But that set of equations is just this set of equations with everything taken complex. So the 2 equations, the 2 sets of equations are identical. Okay? I'm telling you a story that I've not written down explicitly. Okay, is that okay? Hello, hello. All right, try it, okay? Try it, okay? That is the footnote here. Try it out, okay? Now, let's look at the resulting 2 sets of equations. You will see something very familiar. Let's try to write it out as the equations to look for the optimum C1, C2. So 2 equations for solving C1 and C2. It is just like that. Okay? And now if we write it into matrix form, doesn't it look familiar? Look at the matrix element. It is Hij minus ESij. Recall, when we use the complete set, any choice, complete set, to write a Schrödinger problem into a huge matrix, the same form of the matrix elements comes up. It's not accidental because we are doing the same mathematical steps. Okay? But here we relied on variational method to do it. Okay? So now we can have a rather nice connection. Remember last time, in theory, we should use a complete set. The Schrödinger problem should form an infinite by infinite matrix. Now the game is, if we only look for the ground state energy, and if our basis function start off with less wiggling to more wiggling and even more wiggling, we can truncate our matrix to smaller size. For example, infinite by infinite, how about 4 by 4? How about 3 by 3? How about 2 by 2? Okay? And what we are doing in this example is truncating it to 2 by 2. And now we can justify that truncation using the argument of that it is basically a variational calculation if you truncate it that way. Okay? So now we get some rather, this is a very important result, okay? Why is it so? Okay, I just talked about this one, okay? So now, if we show that it is, if you use 2 bases, you get 2 by 2. If you use n bases, you get an n by n. Okay? Nonetheless, you can solve it. All right? Now, if you use 2 by 2, let me go back to here, how to do it. Set the determinant to 0. You will get two values of the energy. If you are shooting at the ground state energy because variational, you pick the lower one. Then you are done. Okay? You pick the lower one, you plug it back to find C1, C2. That will be your best value for your trial wave function. Okay? Even you can draw out the formula. This is the best trial I can get with my form. And that is my best guess of the ground state energy. Extending it to n linear combination of n functions, then you have this bigger matrix. Okay, now for those of you who like derivation, try it out yourself. Okay, now it's not 2, it's n. Okay, and then same thing, determinant of this thing is 0. Will be an nth order equation for E. You will get n values of E. You pick the lowest one, okay? And then you can get the best guess. But more, since we know that this is also related to the truncation of the exact infinite by infinite one, in addition to taking only the lowest energy for the ground state energy, you have reasons to believe that the second lowest one, the third lowest one, they are quite good guess of the first excited state, second excited state of your quantum problem as well. Okay, so now it's not blind guess. We have some theoretical backup connecting this method to the exact problem that we developed last week. And that is why I did that for the first thing in our course, writing anything into a huge exact matrix problem. Okay? So now let me finish this up, and some students would like to promote their physics society to you, okay? Your fellow classmates. That is something that I already discussed. It is related to the truncation of the huge infinite by infinite problem. All right. So later on, we will use this in several occasions. Occasion number 1, why do we have H2 molecule? Last time I draw on this example, you have hydrogen atom 1, hydrogen atom 2. You only want to consider the ground state of this molecular situation. You don't care about some higher energy state. Okay? So, how could you form a wave function for the molecule? The best way is this atom's 1s state, that atom 1s state, form a linear combination and take that as your reasonable guess of the molecular wave function for the ground state of hydrogen molecule. That is a typical situation of linear combination of two functions. At that point, I don't want you to do the derivation again. You just grab the 2 by 2 matrix and start working. Okay? The second occasion, another occasion, I would say there are many more, is that we want to understand benzene. In particular, we want to understand what this circle in the middle is about. You know, benzene is a hexagonal ring. There are some so-called p state sticking out of the plan. How they are bond? A natural choice will be linear combining 6 functions, each from each carbon. You have a combination of 6 wave function as your trial wave function of how this electron, so-called pi electron, will bond themselves. Again, we have this standard situation. Your trial wave function is a linear combination of 6 functions. At that point, I don't want you to do the derivation again. You just pick the 6 by 6 and start working. Okay? That's why this method seems very silly, variational calculation, but I would say it's the most useful method in understanding bonding in molecules. So I want you to practice this in your problem set 1. All right? So at this point, I would like to see whether our the next physics student society, the representatives, are you around?
Yes, we are here.
Okay, you are here. So it is 10:15. I will give you a few minutes to promote your proposed work, okay, to the fellow students. So students, please stay on. They have prepared it for some time, okay? So they are doing some online promotion. Okay, you may take over.
Okay, thank you, Professor.